Okay, good evening. Welcome to lecture 6, which is going to be about virtual machines. We've already seen virtual machines to a certain extent. We're going to define one that is full-fledged for the language simple, which, remember, has functions and recursive functions, right? So it is essentially a Turing-complete language. This is the point where everything about basic programming comes together. So we have a language that essentially has all the usual constructs. We haven't added yet fancy stuff like, say, exception handling, but we have everything that is very basic right there. We don't even have while loops, right? And now we're going to define a virtual machine which is very resemblant of a typical processor, right? And we're going to see how do we compile from simple into this virtual machine language. So this will explain the link that compilers are essentially implementing. Will essentially reveal the mystery of compilers. So as usual, we do this incrementally, right? We define a set of incremental languages, sort of, right? So we're going to start with a language that doesn't even have division. It's pretty much a basic language. Why? Because division by 0 is special, right? All the other arithmetic operations, whenever you provide 2 arguments, they provide a result. Division is slightly different, right? So we're going to see how we treat that. Then we're going to need jump instructions, and we're going to see how the constructs that require that and use such instructions, and then we're going to start looking at functions and explain how recursion is implemented. And finally, we're going to look at tail recursion, which is a very quirky subject. It's essentially an optimization. It's not necessary, but it is very important, especially for functional languages. It's very important for a language that doesn't have while loops. All right, so let's start. We're going to consider this language, which is a language currently of expressions. This is a language that we know very well, and we know the virtual machine for this language, and we know how to compile, right? We use the stack, right? Every time we see an operation, we push the operands on the stack. We pop the operands from the stack, we push back the result. Notice that we do not have division here, right? Previously, we swept this aspect under the carpet. Now, let's remember the basic machine instructions, the basic virtual machine instructions, right? And we define this via inductive rules as well. So, done as a standalone instruction is a program, is an instruction as well as a program, right? Now, if S is a program, then prepending LDCI I to it also produces a valid program. LDCI stands for load constant integer, and the argument I is supposed to be an integer. The effect of that, if you remember, is to load I into the stack. LDCB is similar, just that the argument is a Boolean. Then we have the instruction plus, which pops 2 arguments, computes a result, pushes back that result. And similarly for minus and times. Okay? So everything is relatively easy so far. And we want a translator, right? We want a compiler. This is what a compiler does. Takes from the language simple A, which is just a language of expressions, and returns a sequence of instructions that can be executed by the virtual machine. All right? So there is a quirk here, right, that sort of, in order for things to work properly for us, we actually have to consider sequences of instructions that do not have a done. So in other words, they're not complete programs. As we defined on the previous slide, all complete programs have done at the end, right? But we're going to have to operate with fragments that do not have a done at the end. So we're going to define a relation, this curly arrow here, harpoon arrow, I think it is called, right, that where E translates into S. So E is some expression, and S is a fragment. And we're going to say that if E translates into S, then E fully translates into S dot done. And this fully translates relation represents the full-fledged compiler. We always produce a sequence of instructions that ends with a done. Why is that? Because we're going to, big expressions are made up of smaller expressions. So this compositionality issue is a recurring theme for us, right? Everything is compositional. Everything big is made of small parts. And how do we define anything inductively? Well, we're assuming that we already have the translation or result for the smaller parts, right? We don't care how. And we define a way from those results, smaller results, to build a bigger result for the entire expression, right? So that is a recurring theme. So the fact that we are requiring this done to appear at the end breaks that rule, right? Inconveniences us. So we have to define a helper, an auxiliary thing, which is this relation. This relation will allow me to translate into fragments that do not have the done. Because they do not have the done, when I put them together, side by side, when I concatenate them, they produce another fragment that is still a valid fragment. It's a sequence of instructions, so therefore it's a valid fragment. If the first one would have a done, and the second one would also have a done, when I try to concatenate them together, there will be a done in the middle, which makes this program incorrect. Okay? So this harpoon relation here is a crutch, essentially, right? It's a helper. So we're saying, well, we're going to focus on translating E into a sequence of instructions, right? With the understanding that this E is actually part of a bigger E prime. At the end, when we end up with the E prime that is our overall expression, guess what? We take the resulting fragment, put a done at the end. That's our program. Cool? So let's look at these rules, which we have seen before, right? So the first one is a translation schema, rather, right? It's an infinity of rules there. If small n is a numeric constant, and when I say n as a numeric constant, I mean the sequence of digits, right? So remember, we keep talking about semantic domains here, and we're talking about the realm of math, and then we said before that the sequence of digits is not exactly the number, right? The number is a concept that lives essentially inside our minds, or is something that can have a representation inside a computer, right? But the value of the integer is different from the sequence of digits. And you know that very well, because in any language, you have to translate from string into integer whenever you read a sequence of digits. So this is a similar thing here. We're saying that if n has the value I, so the n would be the concrete domain, which we're not saying what we represent it as, but most typically would be represented as a sequence of digits, right? So if we're saying if n has the value I, then we are translating the program fragment n, and when I say program fragment, I mean simple, into the instruction LDCI I. All right? Now imagine that n would be the overall expression that we have to translate. This is the only thing we have to translate. Our expression at hand is n, right? Then if I take the LDCI I and put a done after it, that's a valid virtual machine program, right? That we could execute and actually and essentially compute the value of the expression n. trivially, right? Because it's loaded into the stack, and what the result of the machine is whatever is at the top of the stack. All right, and this is it's an infinity of rules, because what we really should be writing here is, right, what we really should be writing here is if 0 translates into 0, and I'm going to somehow indicate that this 0 is from the concrete domain, then 0 translates into LDCI 0, right? And then replace that 0 by all possible numbers, right? Which we haven't said that the domain of integers is finite. It would be normally in a real computer, but we haven't made that assumption, right? Because this actually is semantics and works for infinite numbers, so we would have an infinity of rules there. What we express here is a schema. Hopefully that's clear. All right. Things are simpler for Boolean constants because we only have 2 of them, and in this case we indicate both rules. Right? We don't need a schema. And then this is where things get interesting, composition, right? If I have an E1 and an E2, and my overall expression is in fact E1 plus E2, right? So see how we're assuming, I have something plus something else. And by some magic, by some other means, by means that I'm not currently interested in exploring, I know that E1 translates into S1 and E2 translates into S2, right? So what do I do with that? Can I get from that assumption, can I get the result for E1 plus E2? Can I get a translation for E1 plus E2, right? And yes, we can. This is the rule that we're making. E1 plus E2 translates into S1 concatenated with S2, concatenated with the instruction plus, right? And notice how it is very useful to have fragments at this point, because S1 is a fragment that doesn't have a done at the end. S2 is also a fragment that doesn't have a done at the end. Because of that, after S1 I can put S2 and still get a fragment. If I had the done in the middle, that would no longer have been a valid fragment. And then after S2 I can further add the plus. If S2 had a done at the end, done and plus would not have made a valid program. Similarly for times, similarly for minus, which is not shown here, but the rule would be very simple. All right. Similarly for all the Boolean operators, right? So a conjunction is the ampersand sign, and we have an instruction called AND. This junction is the bar, and the virtual machine instruction is OR, right? And further, we have the negation, right? Not the less than, and the greater than, and the equal, and you could potentially add less than equal, greater than equal, not equal, right? Everything would follow pretty much the same principle. All right? Is this clear? Right? So focus on the compositionality here. This is absolutely crucial. All right. So let's go on and all right, see how the machine works. So now we sort of know what the machine, what each instruction does, right? But we need to define it formally. So let's take each instruction and provide a mathematical definition of what it means to execute that instruction. Okay? And this will give you a hint at how you would implement the virtual machine. All right? So what we have, let's go back here. We have a structure, right, of 2 elements, which are typically called the registers. All right? So one is the program counter, and that shouldn't surprise you because you've gone through a computer organization module and you should know what a program counter is. And the other one is the operand stack. Now what really happens inside the CPU is that the operand stack is a reference into the memory, right? And that memory is organized as a stack. It's not that the register is the stack. The register is the stack pointer. Okay? But we're going to sweep that under the carpet. We're assuming that that register holds the entire stack. It keeps things, it makes the things a little bit simpler. It's a simplifying assumption. Okay? We're assuming that we're starting from the configuration where the stack is empty and the program counter is 0. And since it's just two of them, we represent the structure as a pair, and the stack is represented as elements within angle brackets, and the PC, the program counter, is just 0. It's just a number, right? So empty angle brackets means the stack is empty, and 0 means program counter is at the beginning of the program, right? We're assuming that every program is an array of instructions indexed at 0, so first instruction is at index 0. And the end configuration is attained whenever the current instruction is done. All right? So we're going to represent by S the stack of the machine, and indexing S is S round brackets, right? You would expect square brackets, but in this module, we choose to represent the index of the stack in round brackets. So S index PC, S sub PC is done. That's when the machine stops. So the machine will keep going and executing instruction by instruction by instruction. At some point, the current instruction becomes done and the machine stops. And the result is whatever is at the top of the stack in the end configuration, right? So we're saying that the result of the machine S, the MS, is V if starting from the initial configuration, right, and that double arrow star represents the transitive closure, the reflexive and transitive closure of the transition relation of the machine. The transition relation of the machine is the relation that executes one instruction, right? So executing all possible instructions until we are done. At that point, whatever is at the top of the stack should be this V, and this V is considered the result of the machine. Is everybody comfortable with this? So this is something we've seen before, and at that point we have not said a word about division. We had considered division, right? And we have not wondered what would happen if we divide by 0. Obviously, one possibility is to just define our own version of division, where division by 0 just gives you 0, or division by 0 just gives you infinity. We have some special encoding for infinity as a number, right? We enrich the set of numbers with infinity. We can add minus and plus infinity, and we can do that, right? But that's not how virtual machines typically operate. We want to produce a state of error. We want to create a state of error. We want to signal the fact that an incorrect operation has been performed. Okay? So, we're going to create a special value which we represent as this sign for perpendicular, right? This sign here, and we typically call this one bottom. Have you encountered that before? Right? So it's very typical of semantics. It represents infinite computations or error states. It's called typically bottom. And it's called bottom for a good reason, right? If you delve into the theory of semantics, you would find out that they relate to a algebraic structure called a lattice. And a lattice has essentially some sort of a maximum element and a minimum element, right? And the minimum element is typically called bottom and represents nothingness, typically. All right. So this bottom represents sort of an error state. And anything combined with that error state produces a further error state. Okay? So what's going to happen? Let's say I have a big expression and I have a division by 0 somewhere. Right? So I have something like 2 plus 3 divided by 0. I have 3 plus 2 divided by 0. Well, this is going to be bottom. And then 3 plus bottom is going to be bottom. And then anything plus or any other operation with bottom. So this bottom is going to surface up to the top level of the expression, and the entire expression is going to become bottom. And this is how we find out that we had a wrong operation inside our expression. With this mechanism, we don't know yet where it happened, but that can be easily tweaked. Okay? Oh, here. So, if the current instruction is div, this is the first rule, right? If the current instruction is div, right? Remember, whatever is above the line is a premise. If whatever is above the line, if the current instruction is div, then if my operands are 0 and some I1, so if the first operand here is 0, then the result, the next state, right, the next state of the machine is bottom, and whatever else was in the stack here is preserved, right? And so here we apply an optimization. So I'm going to discuss this in a minute. All right, just assume that this is PC plus 1 for the time being. PC plus 1. Okay, for the time being. The alternative is, right, the current instruction is div, and I have two operands here, I2 and I1. This I2 is known to be non-zero. So then then I1 divided by I2 is possible, right? So what we put in is I1 divided by I2, right? Whatever else was there in the stack stays there, and we move on to the next instruction, right? So now, since bottom is a possible value in the stack, one thing we would have to do would be to define the result of any other operation with bottom. I can have bottom plus something, right? The bottom is first produced by the division, but then it's there, so I need a bottom plus something or something plus bottom, right? So I would have to define all the I would have to provide all these rules, right? And that's very, very much possible, and this would be a way to percolate, to transmit the bottom value to the top level result, right? However, we can do an optimization, because at that point we know for sure that the entire result is going to be bottom. So instead of jumping to PC plus 1 here, we're going to jump right to the end. Guess what instruction is at this point? It's done, right? So we're automatically ending the program and making sure that the value, the result of the machine is this bottom that we have put here. Right? So this is an optimization. This will end up the program abruptly, but with the correct result. Does this make sense? Yes? Cool. All right. So we're going to move on to handling if statements, right? Which, remember, they were part of simple. So we have an if, a Boolean condition, and then two branches, right? Those two branches would be expressions, and if the predicate, which is the first part of the if expression, is true, then we return the value of the first expression. Otherwise the value of the second. Okay? So how can we do this? Well, we would have to follow the compositionality that we had before, right? So I'm going to have something along the lines of if expression 1, then expression 2, else expression 3, right? And then this E1 translates into S1, this E2 translates into S2, this E3 translates into S3. And with this S1, S2, S3, I have to somehow make this entire construct work. Now, there are going to be instructions. The only thing I can do with these is to put them inside a bigger sequence. So I'm going to put them inside an S1, S2, and S3. And I'm going to fill in something here and something here, right? I'm going to invent some instructions to put there in such a way that if the result of S1 is false, somehow I can jump to S3. That's pretty much what I want. If the result of S1 is false, I want to skip S2. Because it would be wrong to execute S2 and evaluate S2, right? Now, on the other hand, if the result of S1 is true, I would have to execute S2, but then from here, I would have to skip S3, right? So from here, I would have to find a way to skip S3, right? So this is what jump instructions are for. So we're inventing two new instructions, Joffre and go to R. Okay? The R stands for relative. And relative means that we're jumping with respect to the current position in the program. Okay? So, and these are actually instructions that are available in virtual machines as well as processors nowadays, but they weren't available in the early processors, right? So in those cases, there was things were a little bit more complicated, and we might want soon enough to actually take a stab at solving that problem. But for the time being, let's just work with relative, right? We're jumping relative to the current position. Okay, and that makes it easy because I already have S1 and I know its length. I already have S2 and I know its length, and I know S3 and I know its length. So if I want to skip S2, I have from the current position, I have to jump to a position that is the length of S2 locations away from the current position, right? So that's pretty much how it works. Now the OF stands for on false. And J, you probably imagine by now that it's jump. So jump on false. If the result of the previous expression is false, then go ahead and jump. Right? So let's see why this makes sense. So E1 is the if condition. We have to execute that and evaluate it, right? At the end of S1, at the end of executing S1, the result of S1 is at the top of the stack, right? The jump on false instruction will pop that result, look at it, check if it's on false. If it's on false, it jumps. If it's not false, it continues executing, right? So this makes sense. So if the result of S1 is true, it's not skipping, and therefore, right, if it will just go and execute S2. Okay? If it is false, where do we need to go? Right? So this is my instruction, and I would like to go and start executing S3. Okay? Well, we'll have to look at the definition. Frankly, I can't remember exactly what the semantics of Joffre is doing, but we're going to assume that as we execute this guy, we haven't advanced the PC. So the PC is still on the last instruction of S1, right? And therefore, we have to jump exactly the length of S2 plus 2 locations, right? Plus 2 locations, because since we're jumping from the end of S1, there are 2 extra instructions here that we have to skip. All right? We don't want to perform as part of the instruction PC plus 1 and then the jump, right? We want to jump directly. So it's making it plus 2 is another optimization. Now, the same here, right? When we execute this instruction, we assume that the PC is still at the end of S2. And therefore, this go to R jumps unconditionally, right? It jumps unconditionally. And how far do we have to skip? We have to skip until after S3. No part of S3 needs to be executed, right? So since we're currently, our PC is at the end of S2, we have to skip the length of S3 plus 1. Okay, is that clear? So is this clear? Is it clear how it works? We execute S1, Joffre will pop the result from the stack and check whether it's false or true. If it's true, it just keeps going on, and that entails that S2 gets executed. If the result in the stack is false, it will perform a jump forward by skipping ahead S2 plus 2, the length of S2 plus 2 instructions. Clear? Questions? Right? So I know that thinking of the fact that jumping from the end of the previous instruction, of the previous sequence, that's a weird concept, right? But as you will see immediately in the definition of Joffre, in the semantics of Joffre, and the semantics of go to R, it's simpler to define those instructions in that way. Okay? Yeah. There's a? There's a, it's not a 2. Consider these as having brackets. But those brackets are not part of the language. Okay, so it's S1, right, dot Joffre S2 plus 2. That's actually a very good point. Dot S2 dot blah blah blah, right? So this is a full instruction, and when I'm saying this here, don't assume that this expression is computed as part of the execution. This is known at compile time, right? The length of this is known at the time compile time. Let's say it's 10, and then I add 2. So in the end, what the translation says is that this is Joffre 12, right? The virtual machine will never see anything else but the 12. All right? The expression gets evaluated through the translation process. That makes sense? So it's done by the compiler and not by the virtual machine implementation. Okay? Yeah, sorry, that's a bit confusing indeed. All right. So let's look at an example. We can have an expression of this form: 2 times, if true or false, then 1 plus 2, else 2 plus 3, and, right? And obviously, hopefully this is this is clear. Right, the if statement is one expression, 2 times is outside of the if. Right? So the last operation to execute is the star. So let's see, how do we go about doing this, right? We start from the small expressions, right? So I have a 1 plus 2 here. So let's recognize this, right? So it starts here. We have 1, 2 plus, right? We have 2 plus 3 here. So we have 2, 3 plus. Okay? So now we also have true or false, right? So we have true, false, or. Okay? And now we need to translate the if. So this is the condition on if. This starting here and ending here is the first expression of the if. And this is the second expression of the if, right? So in between, this was the S1, this was the S2, and this was the S3, right? So in the middle, I wish I had a different color. Notice the Joffer and the go-to, right? So if the PC is here at the time of executing this, we're going to have to skip 1, 2, 3, 4, 5 instructions, right? So we end up here. And when we're saying Joffer plus 5, Joffer is not. So the argument is plus 5, because we could also jump negatively. And we're going to see when we implement while loops, we're going to see cases when we jump negatively. So we're jumping by 5, and the plus is sort of redundant. Go to R plus 4, right? We have to skip potentially. We have to skip 4 instructions. So 1, 2, 3, 4. So we end up here. Okay? So then, right, if you think that this is the start of the if and this is the end of the if, right? So we have the 2 that goes here. We have the if starting here, ending here. And then we have the mul. And then we have done. And that evaluates the entire expression. Is that clear? All right. So we have 2 new instructions, go to R and Joffer. So let's see their semantics, because this is another language, right? So this is part of the language. This is part of the language, and also, yeah, the same thing, right? So we're essentially having SVML. This is one language, our virtual machine, and we have simple. And we're looking at the translation process going from one to the other, right? But then we're going to have to essentially prove the equivalence. So guess what? We're going to define semantics for this. We're going to define semantic for this. And we're going to try to argue by the relationships of these 2 semantics that the compilation is sound. It's a sound thing, right? So everything has to close together. So we're translating between 2 languages. How do we know that the translation is correct? Well, I define the semantics of one, define the semantics of the other, right? I see the relationship between the semantics of the original program and the semantics of its translation, and I prove that that's a sound process. There's some soundness relationship between the 2 semantics. Okay, so we're going to get there. But for the time being, we have to define semantics for the virtual machine language that we're talking about. And we have 2 new instructions. Let's define their meaning. So if, what we're saying here, if the current instruction is go to R, how do we define what an instruction is doing? I define the transition that the machine is performing when it encounters that instruction, right? So I'm saying if the current instruction is go to RI, then from OS PC, I go to OS PC plus I. So I don't want to go to OS PC plus 1 and then PC plus 1 to PC plus I minus 1. We just go to PC plus I. Okay? The stack stays unchanged. This is an instruction that does not affect the values that we have computed. It only affects the control flow. It affects which instructions get executed. It has the power of skipping some instructions. Now, let's look at the conditional jump. Jump on false relative, right? So if my current instruction is jump on false relative I, right? Now, if my current state is one that has true at the beginning of the stack, at the top of the stack, then we're not jumping because it's jump on false, right? So we're going to consume the true, right? So here there's no true anymore. And we're just going to continue execution as usual. So we'll go to PC plus 1, just the next instruction. If on the other hand, the current instruction is raw for I, and we have a stack that has false at the top, right? We're going to jump essentially. We're going to consume the false, and we're going to move to PC plus I. Does that make sense? Cool. So there we have another example. So it's an example of execution. So we're taking the program that we saw in the previous example, right? Previous example was take an expression, produce the virtual machine program, right? Now take that virtual machine program and see how we get a result out of it, right? So we're starting, as we were saying, from the initial state, which has an empty stack and points at 0, which is here. All right, and we see all the transitions step by step. So we have load 2, and this should have been LDCI. Sorry for the misspelling. So 2 goes into the stack. We go to the next instruction, right? Then we load Boolean true. So we have true and 2 in the stack, and we jump to the next instruction. We load Boolean false, so we have false, true, and 2 in the stack, and we jump to the next instruction. Then we perform the OR. OR will take the last 2 guys, the first 2, we'll pop 2 guys from the stack, right? We'll compute the result, and we will push back the result, right? And it jumps to the next instruction. And then we encounter the rougher, okay? And because we have true here, this true is consumed, we do not jump. So we just go to the next instruction. After 4, 5 follows. So that's what happens. All right? So then we go and load 1, which is here, right? We go and load 2, which is here, right? 2 plus 1 is 3. So notice that 2 and 1 have disappeared, and 3 goes to the top of the stack, right? And then we have the mul. So 3 and 2 disappear. No, sorry. Then we have go to 4, right? So we jump 4 instructions, right? So from here 1, 2, 3. So we jump 4 instructions. 1, 2, 3, 4, right? Right here. So this is mul. And we execute the so now we have 3 and 2, and we're at instruction 12. All right, and then we execute the mul 6 and 13, And when the program counter is 13, this indexes the instruction done, so we're done. Okay? So everybody is fine with this. It's relatively easy to follow, I think. So, any questions? Cool. So, what happens if we don't have relative jumps? Early processors did not. They could only jump to the absolute address. So, this process has to go into 2 steps. Has to be performed into 2 steps. We cannot get the the absolute indexes, the absolute addresses. I'm going to very frequently call the indices into the program addresses, because that's what you would call them in computer organization, right? The memory has addresses, and the program sits in memory, so it's at an address. It's very difficult. I mean, it's impossible to compute them. Probably impossible to compute them in one go. So we're not going to be able to do it as part of our definition of compilation, right? So we're going to use a crutch as well. Again, right? We're going to use symbolic labels. We're going to use symbolic labels. Then we're going to collect all the symbolic labels. We're going to see a mapping between symbolic labels and addresses, and we're going to replace the symbolic labels by addresses in a second pass. All right? And this led to what was called back then, that was back in the 70s, the 2-pass compiler. Okay? Nowadays compilers have at least 5 passes. But so you would need at least 2 if you want to compile on machines that do not have relative jumps. All right, so we're going to introduce a virtual instruction in a virtual machine, right? So the virtual machine actually has concrete instructions, but this is goes one level further, right? So this is a crutch for us to create a placeholder in the middle of the code. The label instruction does not advance, or only advances the PC, does nothing else, right? But marks the place, a place in the code, which we call by the name given by the label, right? So if I'm going to say go to L2 here, right, go to L2, label L2 is here, right? So this will go from here to here. But later, the intention is to replace this L2 by the actual address. And then this label instruction is going to disappear from the code. All right? And then the problem is that, you see, if I have the S1 fragment, and then I'm going to concatenate it by S2, right? I don't know, at the point of creating S2, I don't know the length of S1. So I cannot possibly know the numeric address that should go here. I don't know where this code is going to be placed in the bigger picture, right? So at the point of creating S2, it's impossible to know the actual value of L2. So I'm going to leave it symbolic. I'm going to say I have to jump from here to here. But then once the entire program is laid out, the label is a placeholder, and I can go and replace labels by numbers. So, all right. So this is an example, right, where we use symbolic labels. And instead of using Joffer and go to R, we're using directly labels. Actually, let me go back and explain. And actually, this rule might be clearer than the previous rule where we were using relative jumps. All right? So, again, we have 3 pieces of code. E1, E2, E3. Okay? And then E1 translates into S1, E2 translates into S2, E3 translates into S3. We have this thing here called, we say it's fresh. We have fresh labels. We can always invent names that we haven't seen before, right? That's a relatively simple thing. Every time I need fresh labels, so I use the word label followed by a number, and every time I need a new label, I just increment that number, add it to the word label, and produce a new label, right? So it's very easy to produce completely distinct labels on the fly. So we're just saying that this L1 and L2 are labels that we haven't seen in any other part of the translation, because we don't want name clashes, we don't want label clashes, right? So then this, if E1 then E2 LC3 translates into, well, first evaluate S1, then if this guy is false, jump to L1, and L1 is here. So if it's false, we have to skip L2 and start executing S3. Otherwise, we allow S2 to get executed, to get evaluated, and at the end of S2, we want to skip S3. So we're going to jump to label L2, which is right at the end. Okay? And this probably makes the translation a little bit clearer than before, where we actually had to figure out that the numeric expressions for skipping instructions were correct, were corresponding to the length of the instruction sequences that were there. I think this makes things a little bit easier. Is this clear? So we have another example, which is actually the same example, but notice now how we don't have numbers anymore. We have just labels, and we are placing labels inside the code, right, to mark a specific instruction. We don't know beforehand what the value of the label is, but what we want, so this is now the complete program. What we really want at the end of the entire compilation process is that, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this L0, we want to say L0 is 10, 11, 12, 13, right? So we want to say that L1 is 13, right? And then once we have found out the values of these labels, we want to go here and say JOF 10 and go to 13, right? We actually don't want the labels in there, we want the numbers. And this can be easily done through a second pass. So once we have the program with the labels, I can go and find out which addresses those labels correspond to, and then go inside the instructions and replace the labels by numbers. Clear? Oh, and there you go. I think I misnumbered. Oh yes, I misnumbered because I started from 1 and I should have started from 0, right? So the labels are actually 9 and 12. And what we really want is the numbers. Right? So that can be done with what we call a second pass. So the result of the first pass is the program with labels. It's the result of applying the rules of compilation. And the second pass is just a scan through the program. You start counting, and you reach this point, you say, oh, L0 is 9. You reach this point, you say, oh, L1 is 12. So through this pass, you keep placing all the, you keep creating a table of mapping, a mapping from labels to addresses, and then you use that mapping in order to generate the numeric codes. Okay? So what are the rules for the new instructions? They are very easy. They're a lot easier, right? Because now we have absolute addresses here. So all I have to do is just set that address. Say if I have a go to I, the PC, the program counter, just becomes that value I, right? For jump on false, whenever we jump, which is here, right? Here we jump, we just set that the PC to that value. That's all we do. Cool? All right. So let's see what's next. We have a new language. We have a new increment to the language, which is functions. So functions come with three new elements, three new constructs. One is the variable, two is the closure, the lambda, and three is the application. All right? So I have to be able to define a function and apply a function. And in order to define a function, which needs to have arguments, I need the concept of a variable. When we use variables, right, the important concept around variables is that of binding. A variable which is used somewhere has been defined in a very precise place. And we always want to match the use with the definition. All right? And that gives us the concept of scope. The place where the variable is defined, right, the place of definition, the declaration of the variable, gives us the realm where it is accessible. Right? In this case, the realm is inside the expression E. So any variable here is accessible inside E. Any reference to the variable outside of this function is illegal. Right? Now, a supplementary problem is the one of name clashes. We can use two different variables with the same name. One in an outer scope and another one in the inner scope. So whenever that is the case, the most recent definition prevails. Right? So if I have something like fun x goes to fun something, fun x e, and here, and here, right? Any instance of x inside E refers to this x and not this x. Is that clear? Yes? So that's a potential complication for us. So that's most programming languages go by this rule. There are some programming languages that will as part of type checking would reject this kind of situation. One being Java, right? So Java does not allow you to redefine an outer scope. Most languages nowadays would at least give you a warning. But you still have the problem. If it's a warning, it's still legal. You still have the problem of handling this correctly. What's a good solution to handling this problem? Well, renaming this internally to something else, x prime, right? And then the clash disappears. But this will be a complication for us. Brace for it. Okay, cool. Now, remember the compositionality. We're creating meaning for bigger expressions from the meaning of the smaller expressions. Right? So, you see, this is the smaller expression and this is the bigger expression. So, the meaning of the fun will come from the meaning of E. The trouble is that when I look at E alone, X will appear without a binding. It's unbound. Right? And I cannot. So my rules of compositionality will say you have to derive a meaning for E in isolation. You don't have to look at its context. You have to do something with that X that appears inside without knowing when it's going to be defined. Okay? So what's going to be the mechanism for that? Well, put it somewhere in some sort of mechanism of keeping track of it. And as I go from the smaller expression to the bigger expression, check at all times all these variables that I keep track of, which are currently unbound variables, check that the bigger scope has a binding for them. all right, and match the bindings. And if when I finish and get to the level of the biggest expression that I have, if I have an empty set of unbound variables, it means that I'm okay, right? If I finish with any unbound variables, I'm not okay. But if I finish with all the variables being bound, I'm okay, right? So in the process of analyzing expressions with variables, I'm going to collect all these variables into some collection of unbound variables, which we call an environment. Okay? The environment will also keep track of the values of the variables as they are defined, because as these variables are bound, that's also a mechanism of providing values for them. All right, hopefully this clarifies. So we have quite a few things to cover here, right? We have to compile identifiers, we have to execute, we have to compile function application, we have to compile function definition, and each of these things needs to be executed. And then at the point of completing the execution of a function, we have to return a value to the outer environment. Okay? So we're going to try to go through all these. So, new component added to the state. Previously we had the stack and the program counter. We get a new register, which we call the environment. Again, we think of it as being the entire collection, even though in any sensible implementation there's going to be a reference to a memory area that is laid out to contain a mapping between variables and their bindings. All right, load symbol. LDS is load symbol, and in simple, X as a standalone symbol, it's a valid program, it's a valid expression, right? And its compiled form is LDSX. We're loading X into the environment. We're creating a slot for X inside the environment. Later, we're going to be a lot more precise about the way we hold this environment, right? Because this environment is laid out in memory. So every variable is going to have a memory address, and we want those memory addresses to have numbers. So we're going to go there at some point. Brace for that as well. Now, we have a stack machine, right? So our way of dealing with operands is a stack. So the function should be no exception, right? A function is essentially the function application, right, which is what we're translating here. We're assuming that this evaluates to a function, and these are evaluate to the arguments to the function, and we're calling E with the arguments E1 up to En, right? And we can think of this space here as being an application operator, the call operator. And based on the way we defined all the other operators, we're not going to make a difference here, right? So we're going to have a function call, an instruction call, and we're going to say how many arguments the function has, right? So we evaluate each of these guys one by one as before. Each of them, right, is a sequence it's a sequence of instructions. We lay these instructions importantly in reverse order. All right, that's very important. And then the call is going to, why? Because we want this one to be at the top of the stack. If I put them in direct order, I don't know where the function is, right? I don't know where the object representing the function is. If I put them in reverse order, what is at the top of the stack represents the function. And then I say call n, meaning that I'm going to have n arguments. So I take n plus 1 elements from the stack, I pop them out, and essentially we're going to have a mechanism We're going to see the semantics of this. But we're going to have a mechanism by which we invoke the result of S, right, with arguments representing the results of S1 up to Sn. Okay, so we're going to define the call instruction shortly. Okay. Now, when we have a function definition, right, we would have a translation. Let's say that the translation of E is S, right? So we have this concept of free variables. Free variables are unbound variables, right? Variables that are undefined. We call them free. Okay? So this E can have many variables appearing inside, many free variables, right? But only x1 up to xn are going to receive a binding, right? Through this definition, x1 up to xn will have a binding, right? And this is very simple to conceive, because I could have a fun x that goes to fun y that goes to x plus y, and, right? So if you look at this expression, this x appears free. So this function definition, which may be this one, we don't know that this is the outermost. This is a function definition that is happening, so it could be this one. So when I'm at this level, I see a binding for y, but I don't see a binding for x. X remains free, right? So I want to look at this set that contains all those variables that will continue to remain free after this definition. Okay? So if I take this as a standalone, this will be a function definition where x, this is x, sorry for my handwriting, continues to appear free. If I look at this expression, which would be the E here, right? X plus y are both free. As I go to the level of x plus y to the level of fun y x plus y, y becomes bound, x continues to be free, right? So this set would contain the x. This set would contain the x and y. But the y becomes defined, so we subtract it, and what we have in VS is the x. Does that make sense? Cool. So, this is a function definition, okay? There's no execution for it. All right? So, I'm going to so I have a fun, right? I'm going to have a let, very likely. I'm going to have a fun, right? Or somehow, and I'm going to go past this, and I'm not executing anything from here, right? I'm just going to record the fact that the function exists, right? Therefore, I don't have to execute it. Therefore, we are compiling S and laying it out in memory, all right? But we're going to skip the execution, because we're not executing, we're defining the function. The execution happened on the previous slide when we applied. Okay? That's tricky. Right? So one very important thing, will be at a later point when we store this value, right? We're going to be to record this address in here in a place that is associated with a symbol, so we can call this function. But currently, we're just defining the function, right? So the code has to be laid out in memory, and it is laid out right here, but we don't execute it. So therefore, we skip it. We don't even know what are the actual values of x1, xn. Okay? So, this LDFS loads two types of symbols, right? Loads, so this LDFS loads a function, right? It says load function symbol. And when we load function symbol, what we want to provide in the environment, and we're going to see when we discuss the semantics of this, what we provide to the environment is the bindings plus the variables that are still free. Okay? Those bindings plus variables that are still free, they are referred to by this code. All right? There will be LDS instructions on both x1 up to xn and vs. And one thing we want to make sure is that all these LDS can execute. Meaning that whenever I do an LDS, the environment has a corresponding mapping for, so I'm going to do LDS, let's say variable z, and my environment has to have a mapping for that z. Right? Okay, so keep this in mind, right? We're going to go back to it. We're going to try to go back to it. So everything closes at some point, right? We're making a lot of assumptions of what we're going to define in the future, right? And then we have to be held to that promise of defining all the right things. So everything has to close. I'm going to define a few things and then come back here and show that everything closes. Okay? So, just to make it very clear, this is the function. And it's been laid out in memory. I want it to stay there in memory as a sequence of instructions. I want the sequence of instructions to be available for me. But I'm not going to execute it right now. So from here, I'm going to skip right to the end for the time being. Somehow, later, the start address of this function will be made available so that I can go to, when I do the call, right, I'm going to be able to jump here and execute those instructions with a specific set of bindings for the arguments. Okay? So keep that in mind. Park it in your mind for the time being, and let's focus on what's next, and then maybe we come back later and show that the circle closes. Now, we can do a similar thing with labels instead of using relative go-tos. Okay? And that's in no way surprising, right? We set labels and we just use those labels. All right? What we want is to skip the body of the function for the time being. So the go to L goes right after the return instruction. You see a return there. RTN stands for return, represents the return from the function. It's equivalent to the return that you're using in languages like Java, JavaScript, C, I don't know, many others, Python, and so on. Not Scala or Haskell or Ocaml. All right. So let's try to see how we execute this. Right? So remember, by doing this LDFS, all right, we're preparing the ground LDFS was used here, right? We're preparing the ground for a definition of a function. Okay, so let's assume that our current state is OS, PC, and E. And our current instruction is this LDFS, which has a bunch of free variables and a bunch of bound variables, so a bunch of variables that are about to be bound, right? x1, xn are the arguments to our current function. Okay, so what I try to do here is define a function. Now look at the very specific way we're compiling this function. So the start of the function is here, which is 2 instructions away from here, right? So the start of my function is at PC plus 2. When I'm executing this, the start of this instruction, the start of my function is at PC plus 2. So I'm going to take advantage of this, and I'm going to say, well, so this is this is going to be the new environment. Oh no, so sorry. The environment is here. This is the environment, right? This is going to be my new stack. So we're going to define a new type of values for the stack. That type of value represents a closure, a function, a lambda, right? This record represents a function. What do we need in that record in order to represent the function? One is the start address. And based on our compilation scheme, right, the start of our function is going to be 2 instructions away. So I'm going to say PC plus 2. Right? That was in the previous slide. So we have the LDFS, we have the goto, and we have the start of our function. So the start of our function is at PC plus 2. All right? And you're going to ask, how can I make sure that it's always 2 instructions away? Actually, I can't. But we're just going to assume that nothing goes wrong, right? There's nothing in the formalism that enforces the fact that the instruction is 2 away. It's just by virtue of declaring that rule on the previous slide and using no other rule that I believe that it will always be the case that the start of the function is 2 instructions away. Then I need my set or sequence of arguments. And then I need to capture the current environment. So if you remember the concept of closure, right? You define a function, and all the variables that are outside of the scope, they are sort of linked into the function. That's why we call it a closure, right? So we need to store those extra variables that are still unbound, so we know where to get them from, right? So we're going to take the current environment and project it with respect to the variables v1 and up to vm that continue to appear free in the function after these bindings have been performed. Okay? And I'm going to give you an example of why this is necessary. Right? So let's pick a programming language and make this argument. Why is this necessary? Okay, so we could pick Python, for instance, and all right, and let's define function f that maybe has no arguments. And then inside, I'm going to have an x equals 10. And then I'm going to say def g, which doesn't again have any argument, or let's have an argument here. Has an argument y, and then I'm going to say non-local x. Oh no, non-local. I'm forgetting my Python. Do I have to say global, or how do I access outside of scope in Python? Who can tell me quickly? I think if I say return y plus x, this is not going to work. And then here I would say return g, right? Oh, that actually did work. Let's see if it actually works. So I'm going to say a equals f, and then if I say a of 20, I'm going to get 30, right? So you see that value of 10, of x being 10, has been locked inside. Is that clear? Right? If I define another x here, a applied to 20 will still return 30. This x, the x that I use here, will always be locked to this x, no matter how many other x's I define, right? Whenever I call a, that x is going to be in there. Actually, we can do a more interesting thing. Let's define again f, and let's have x equals 10, and then define g, and then as part of g, I'm going to say result equals x plus y. Then I'm going to say x equals 2 times y, and then I'm going to say return result. Okay, then return g. Okay, so now I can say again a is f, and then if I say a applied to 10, x is referenced before assignment, so that's where I have to that's where I have to use non. Let's see, do I have a sublime here? So Control N, Control V, we'll get rid of this. The thing is, I don't know where I'm going to be typing tabs or spaces. I also don't have an internet connection because I forgot my dongle. So do I say here global x? Non. But why didn't it work here? Oh, did I use Python 3? I might have not used Python 3. So So let's use here non-local. All right, so again, A equals F, and then I'm going to say A10 or A1. I'm going to get 11, right? So the value of X was 10, right? But now if I'm going to say A applied to 2, what value do we return? What do we expect? Returning 4, right? Why? Because in the process of using 1, I have made the X being 2, the double of 1. Right? So that X is locked in there. This X will stay with the A forever. All right? I'm using it as storage. Does this make sense to everybody? So in the process of creating this closure, you see what this F is doing is defining this G and then returning it. Right? In the process of returning this G to the world outside of the F, we're locking the X together with the G. Right? So at the point of defining G, if you look at the G closely, X is free, is unbound, right? But nevertheless have to be locked together with G. This is why we have to capture the bindings. So Y is the binding of G, as well as the free variables. Because they're locked together, they will be used in the computation. Does it make sense? Yes? Everybody's happy? So going back to the slide, right? The x1 up to xn is the y that we have here, right? And the free variables, the vs, is the set of x. And as I look at the body of G, I'm noticing two variables, actually three. There's the result in there as well, right? We don't yet have assignment, but so let's focus only on the x and y, right? So we see the two variables x and y. Y is bound because it's the argument to G. X is free, it's unbound, right? It is defined outside of G. But whatever I do with x inside, I have to have a reference to where it is defined. So this is why it becomes part of the definition. Cool? So we're capturing the arguments, and we're capturing that part of the environment that has mappings for v1 up to vn, where v1 up to vn are the free variables coming from that vs. Cool? So this is what the instruction provides. How are we going to know? Well, how are we going to know which are the v1s up to vm and which are the x's? Right? Well, we are building them up as we build the compilation of E, right? So previously the compilation of E was a very simple thing because we were just working with constants. Now every time I'm going to encounter an expression containing variables, every instruction that contains a variable will also put that variable inside the environment and creates an expectation of that variable being defined at some point, right? So whenever I have the compilation of E, that comes with all the variables occurring inside E, right? And that's the free variables. This is the free variables that we talk about here, right? So each E from this point on, apart from getting the compilation, also comes with that set of free variables. So that set of free variables in E, part of these free variables are going to be bound, these are the x's, and part of them are going to remain free. So if you look at the previous example, right, inside the body of G we have x and y, both of them free, but as soon as we go to the scope of G, the y becomes bound, but the x stays free, right? So the y will be part of this set, whereas the x will be part of this vs. Okay? And now as we define the function, we have to keep track of these two sets of variables. Now this is a relatively innocuous, so it defines a function. And then notice that what we have put here is everything we need to execute that function at some later point, right? We have the start address, so we know where to go when we are about to execute. We know what to bind when we have when we receive arguments. So if you think of the call instruction, right? The call instruction will give me a parameter n, right? And it will take the n plus 1 elements from the stack, right? One is the function, so will be this guy, this triple that you see here. That will be the function, the s. And then the s1 up to sn will be the argument, the values for the argument. So then what are we going to do? Create a mapping from x1 to the argument 1 from the stack, x2 to the argument 2 from the stack, right? And then these x's get values at the time of the call. Without those values, we can't execute the body. Now, this environment already gives me the values of the free variables. Those free variables must already have values. Okay, that's very important. They must have values at the point of the definition. They can't get values at the point of the call. So we are storing whatever values they are in here. So this triple here that goes at the top of the stack has everything we need to execute the function later. And because of that, we have effectively defined the function. We know the address, we know what arguments we need to bind. So, because we have added this at the top of the stack, we can just move on to the next instruction. So the next instruction is going to be pc plus 1. And this doesn't change the environment in any way because we haven't defined any symbols. Cool? So again, it's a bit of magic here because I haven't told fully the story of what's going to happen with these arguments, with the x1s and with the environment, the free variables. So again, the circle has to close. All right. So now what's going to happen? We're going to go into executing the function, right? And then I'm going to hit the return. Where do I go back? So let me present you with the situation in a graphical way, right? So this is my program. If I only knew how to draw horizontal lines, right? So what we have done is define this function, which is laid out here, but we are executing somewhere here, right? And the advantage of a function is that it can be called many times from many places. So we're continuing execution. At this point, we want to invoke this function, right? So we're going to jump from here up to here. And the understanding, what we know from regular programming languages, what happens when we execute is that when we reach the return point, the final point, we should jump right back. And then from a different point in the program, right here, we're going to invoke the same function again. And when we hit here, we're going to go right back to the point of the call, which is different from this one, right? So the question is, does our state currently have something that enables us to do that, to remember where to go back? Okay, and the answer is no. We need another element. So we need a new type of stack. So we need a new type of stack. And why a stack? Because from inside one function, I can call another function, which can call another function, which can call another function, and I have to remember all the returns sequentially. I have to be able to return sequentially back from every function up to the initial top level point, right? So the only way to handle this correctly is if I remember all these return places in a stack. So the first function puts in a stack. From inside the first function, I go to the second function, And when I'm about to go to the third function, I push in a stack the return place. When I'm in the third function, maybe I call the fourth, so I put in a stack. So then the fourth function returns. Where does it return? It pops from the runtime stack, whatever is at the top, and knows how to return into the third. And then when the third hits return, it pops from the stack and knows how to return inside the second function, and so on and so forth, right? So the idea of having a function is quite clear. So at this point, it's good to make a distinction. So when we talk about CPUs, we often talk about the processor stack. Stack that has a stack pointer, typically called SP. All right. Which stack is this? Is the OS the stack that we were just talking about? No, it's this runtime stack that we're about to execute. So processors will have a stack for calls and returns. The OS, which is the operand stack, is specific to the so-called stack machine, which therefore needs to have two stacks, right? Instead of this operand stack, what do processors like the IA, the x86 have? So the x86 doesn't have an operand stack. What does it have? Anybody knows? Have you heard of the RAX, RBX? No, you've never looked at the output of a C compiler. Right? So it has general purpose registers, right? Which, if you want, you can organize as a stack. There are 16 of them inside the Pentium. Well, Pentium is x86 nowadays. There are 16 of them. There are other processors that have more, but generally, an architecture where you have general purpose registers, which are more like global variables than a stack, that's more common. In general, compilers can optimize a lot more aggressively when they have that kind of internal storage. All right. There's no problem in seeing these registers as a stack if you so want in your compiler, but stack machines are not very common. Stack machines are much more common as virtual machines. So the Java virtual machine is a stack machine, right? It has an operand stack. So remember, there are now, from this point on, we actually have two stacks: the operand stack, the runtime stack. The runtime stack is what we typically refer to as the stack in a processor, right? So that stack is used for returning from function calls and for exception handling and for a bunch of other stuff, which will actually, some of it will experience throughout this module. Okay, so I'm looking for a good time to stop, actually, because it's coming to the end of the class, and I'm already seeing that you're too tired to continue to follow me. So let's see if this should close the circle. So let's go through this slide and try to close the circle. So let's do a call, right? So we have function definition, which is the LDFS, load function symbol, and the counterpart is the call, right? And the two definitions should match and close the circle. So let's try to understand this, and we can finish for today. So the result of the function definition, right, is a triple here that tells me essentially everything I need to know when I want to execute a function, right? So at some point in the past, this function has been defined, right? A definition for this function has been encountered, and the result of that was a triple, and somehow this triple has made its way to the top of the stack, right? So the assumption is that the stack contains, whenever I encounter a call, right, the stack contains a triple that represents a function. Otherwise, I can't call that object, right? And then I would want to have an arguments, right? But guess what? Guess what? I only have m arguments defined in here. So these would be how many actual arguments do I have? All right, and these would be how many arguments have been defined. Okay, so why is this important? If we go back to the example that I showed you on Python, okay, and actually let's go there for all right. So the function f, I could call it like this. I could say actually not even having an x, f nothing and 2. All right, so notice that essentially I'm passing to f 2 arguments. I'm passing void immediately followed by 2. However, if you look closely, f only takes one argument, which is void, right? Doesn't know how to take 2 arguments. It so happens that it returns a function that further can consume 1 argument, and because of that I can allow the writing where f is called with 2 arguments, right? And I know that you're going to say, oh, well, but there's brackets there. Well, in what we're using is a curried language, the brackets are not there, and there's no distinction between 2 arguments, right? There's no distinction between f2 and 3 and f2 and 3, right? But we're in a situation where f can only take the first argument, but the return value of f2 is another function, which is g in our case, and that function g can further consume an argument. So this writing f2 and 3 is legal, but what will happen through the call is that I'm going to consume only 1 argument. Okay? So I have only m arguments here, but at the call place, at the time of the call, we're saying I passed to you n arguments, which is a larger number. It has to be larger, right? So what's going to happen now? Notice we have a new element of the state, which is the runtime stack. So my operand stack, remember this is equivalent to the expression e, e1, en, n bigger than m. All right, all these have been evaluated into s, s1 up to sn, and all of these are in the stack. So this v1, all of these are in the stack. So this os contains v1 up to vm are here, right? So this os contains s1 up to sn, right? So s1 up to sm are v1 up to vm, but this os may contain other s's up to n. Okay, so this is at the top of the stack. We're doing the call. So as with every operator that we execute, it's just an operator, right? It's an instruction. With every instruction, we pop something from the stack, we compute a result, we push it back, right? Or we push something back or nothing back. No, we don't always have to push something back, but we always pop from the stack, right? That's where our arguments are. So we're going to take m plus 1 arguments because we have defined m arguments in here, right? So I'm going to take the function plus its m of its arguments, and I am going to create a new environment. Okay. So first of all, what's the next state? I'm going to jump to the address. This address goes here. Previously there was some PC here, right? I'm going to jump to to this address, right? So remember what happened at the compilation time. The function was laid out somewhere here. My current PC is somewhere here. This is my PC, right? But at the point of defining this function, I stored this address, the beginning, this A, I stored it in here. So now it's time to jump there. We skipped this at the point of the definition, but when I get here and I get the call, now I have to go and execute. So this is when we jump to the address here, right? Now, I am going to execute the body of the function. The body of the function has the variables x1 up to xm appearing inside, which are the arguments to the function. These arguments need to receive value at the time of the call. So we're extending this environment, right, with values for x1 up to xn. x1 takes value v1, which is here. xm takes value vm. So at the point of the call, those arguments appearing inside the body, now they have values. So I can go and execute the body, and I'm going to have values for those. So I'm not going to be at a loss on how do I compute anything. Right? Now, which environment am I going to use at that point? I can't use this guy. I can't use this guy. I'm trying to put a cross on it. So you see, at the point of when I was here, I have an environment already. This environment tells me what the current variables are, right? But I'm going to go inside the function. So remember the situation where I had a global x whose value was 100, and I had a local x whose value was 10, and then the value at the time when I invoked the function, the value that was used for x was 10, right? Was the local value. So the global x would be here, but the local x would be here, right? So I can't use the global E, the global environment. I cannot use this one while I execute the function. I have to go back to the environment that was locked with the function. And this is why we have put this environment here. This one contains the free x that is inside the bigger function, inside the f, right? This x doesn't appear inside g, rather appears in f, or is defined in f, right? So I have to plug it from here. So what I'm going to do is, this x already has a value while in here. That value of 10 has already been locked in. So I'm going to take this one and extend it with my arguments, and now I have values for everything that is inside the body of the function. I can go ahead and execute, right? One major concern is to not leave any value, any variable without a value. So now I'm sure that I have values for every variable. I can go ahead and execute. Okay? Now, I have my operand stack, which has just lost its function because I called it, right? That doesn't need to be here, be there anymore. I have my new PC, which is here. I have my new environment, and this runtime stack has to store everything that appears to be lost, so we can go back. So if you look very carefully, at this part, up to here, and then at this part up to here. You see, going from this part to this part, the PC seems to be lost. In this part, I don't have the PC anymore. I'm going to explain up to here, right? So in this part, I have three elements, 1, 2, and 3, right? The environment, and here I have three elements, 1 up to here, then PC, then E, three elements, right? So as I compare those three elements, it seems that I'm losing information. The runtime stack was not there previously, right? So if I didn't have a runtime stack, what I want to show here is that I would have lost information. So the PC doesn't appear anywhere in the first three elements. So if at any later point I want to go back to that PC, currently there's no way to do that. This E also appears to be lost. Right? If I look here, I have this E prime, which comes from here, and the old E seems to be lost. So if I want to return from the function, I will definitely need to know the PC where to go back, and the E to remember the old values of the variables that I had in that context, right? So I have to put those somewhere. And that place is going to be the runtime stack. The new runtime stack is exactly the place where we are going to put this information that appears to be lost. I'm going to put the E here, the old E, so I can restore it later. And I'm going to put the PC plus 1. I don't want the PC because I'm going to return to the instruction that is immediately after my call, not into the call. Otherwise, I would create an infinite loop. Now, there's another piece of information that we store in the runtime stack, which is the number of arguments that are still left in my call. Why is that? So remember that we had the f applied to 2 further applied to 3, right? Or f to 3 otherwise in our curried syntax. All right? So what's my result of f2? If I have this syntax, the result of f2 is what? A function, right? So what happens with results? They go to the top of the stack, right? So my expectation is that when I'm going to be done with the call, right, I'm going to get this OS with another triple in front of it, because the result of f2 is a function. The result goes on the stack, so necessarily as I come back, right? So at that point, it's going to be important to know how many more arguments to give to this function, because this is another call. The immediate instruction after this is going to be another call, right? So if this number is not 0, what I will necessarily have to do is immediately go into another call, right? If this number is 0, then I can just continue happily execution from PC plus 1 on, right? So the way we handle this record here is when we encounter the instruction return. The instruction called return, the RTN, is the instruction that is going to do something with that record. Is that clear? Okay, but we're going to talk about that next time. Questions? So what I would like you to do is try to look at these two slides, the LDFS and the call, and see that the circle sort of closes. And then also look at this instruction. Yeah, either of these two slides, and the slide that defines the semantics of LDFS, and understand that there's a match there, right? It's very important that the layout is of this format, right? The layout is of this format, right? With 2 instructions before the S. And the existence of these 2 instructions is linked to the fact that we have a 2 here, because that's where the start of the function resides. Okay? Does it make sense? So we're going to reprise this over-applied function, this concept of over-applied. So we looked at under-applied functions. We're going to look at over-applied functions as well. And then we're going to discuss the return, but let's do that next time. Maybe I'll go through these 3 slides for LDFS, call, and return in one go again, so that we solidify that knowledge. yeah, so we're going at a slower pace, but looking at your reactions, it seems that this is the right speed to go at. I'm hoping that you will understand the stuff as you are in class, and you don't need to go through it and be frustrated by going through it alone later. Cool? Everything okay? Questions? It's literally the last class of the week, right? You couldn't be more rested for it.